So in this video, we're going to discuss an important theorem that allows us to actually calculate the value of a definite integral by hand. So previously, if we wanted to find this from 1 to 4, 2t dt, we talked about how you could use your graphing calculator. And if you use your graphing calculator and you plug that in, you'd need to use x's instead of t's for the variable. But you could plug it in, and the result would be that your graphing calculator would tell you that this is 15. Well, we're going to talk about a way that we can actually compute this value by hand and what it tells us about some important relationships that we've actually previously discussed when we looked at position versus velocity. So let's talk about what the fundamental theorem of calculus actually says. It says if f is some continuous function where a is less than or equal to x is less than or equal to b. So we want to look at some area under the curve from a to b. And this is the important part. The function that we're trying to integrate equals the derivative of some other function. We call that function uppercase f. So if we take the derivative of something and it gives us f of t, then we can do the following. The area under the curve from a to b of f of t dt equals the uppercase function with b plugged in minus the uppercase function with a plugged in. So what does this mean in words? What this is saying is to find the definite integral of some function from a to b. Find some other function so that when you take its derivative, you are getting the function you're trying to integrate. You then plug in a and b and subtract them. So let's look at how to do this using that example that we just did. So previously, in our last example, we said the area from 1 to 4 under 2t dt equals 15. And that came from our graphing calculator. So the function that we're trying to integrate, f of t, is 2t. What we want is some uppercase function that when you take the derivative of it, you would get 2t. The function that you're probably thinking of, or hopefully you're thinking of, is t squared. If you took the derivative of t squared, you would get 2t. In other words, f prime of t would give you f of t, which is 2t. So our uppercase function is t squared. So when we're trying to do the area from 1 to 4 of 2t dt, what we're actually going to do is plug in 4 into, we're going to plug 4 into this function, and we're going to plug 1 into this function, following the fundamental theorem. So plugging in 4, we'd have 4 squared, minus plugging in 1 squared. The area from 1 to 4 of 2t dt equals 16 minus 1, which is indeed 15. So it worked. Let's look at another example. Let f of t equal f prime of t. Write the integral from a to b of f of t dt and evaluate it using the fundamental theorem of calculus. So we're given uppercase f of t equals negative cosine of t. Well, the lowercase function f of t is going to equal the derivative of the uppercase function. If we did the derivative of negative cosine t, well, we know the derivative of cosine is actually negative sine. So we have negative sine is actually positive sine of t. So that's our f of t function. We know a equals 0 and b equals 2 pi. So now we can write this definite integral. What we're actually trying to do is the area under the curve from 0 to 2 pi of sine of t dt. So what we're going to need to do is plug in 2 pi and 0, 2 pi and 0 into this uppercase function to evaluate this definite integral. So we're going to have negative cosine of 2 pi minus, I'm running out of room here, but negative cosine of 0. So continuing on, I'm going to give myself just a little more room. From 0 to 2 pi sine of t dt equals negative, and cosine of 2 pi, the x value of 2 pi is 1, so minus 1 minus negative, well, cosine of 0 is also 1. So I've got negative 1 plus 1. The area under the curve of sine of t from 0 to 2 pi is actually 0. And that's because you have that loop that's above the curve until you get to pi, and a symmetrical loop below the curve until you get to 2 pi. So this definite integral is actually just 0. Another example. Let's say we want to differentiate x to the 5th plus 2x. Well, the derivative of x to the 5th plus 2x, the derivative of x to the 5th will be 5x to the 4th. The derivative of 2x is 2. So if that's the derivative of x to the 5th plus 2x, really I could think of this as the uppercase f of x function, because when I take its derivative, I get f of x to the 4th plus 2 as the lowercase f of x function. So then if I wanted to compute this definite integral from 1 to 3, 5x to the 4th plus 2 dx, I want to plug it into some function that when I would take the derivative of that function, I would get 5x to the 4th plus 2. Well, because of part A, we know we really want to plug in 3 and 1 into the x to the 5th plus 2x. So plugging in 3, I'd have 3 to the 5th plus 2 times 3 minus plugging in 1, 1 to the 5th plus 2 times 1. If you evaluate the left side, you get 249. If you evaluate the right side, you get 3. And so the area under the curve from 5x to the 4th plus 2 from 1 to 3 is actually 246. So let's think about an important idea. Velocity is the derivative of position. This means v of t equals s prime of t. So the following is actually true by the fundamental theorem. The area under the velocity curve from a to b of v of t equals the position at time b minus the position at time a. You could think of this as the finishing position and the s of a as the starting position. Well, if you took your finishing position and subtracted your starting position, you might think of that as possibly the distance traveled, or in other words, we call this the displacement. The finishing position minus the starting position would tell you how far the object is essentially moved from the beginning to the end. So the definite integral from t equals a to t equals b of velocity tells us the distance an object traveled during that time, or really moved during that time from start to finish. So So let's look at an example. Let the velocity of a particle be v of t equals 3t squared plus 2, where velocity is given in feet per second at time t. What is a possible function for the position of the object s of t? So it might be a good opportunity to pause this and try and think. What would be s of t? And what you need to think to yourself is s of t is going to be some function that when you take its derivative, you would get velocity. So looking at that velocity curve, what's a possible function for s of t? Well, hopefully you thought to yourself, okay, if you took the derivative of t cubed, that would give you the 3t squared. And if you took the derivative of 2t, that would give you 2. So s of t equals t cubed plus 2t is a possible position function for that velocity function. And you'll understand, hopefully in the future videos, why I'm saying that's just one possibility. There's actually multiple possibilities. Okay, so in part B, what will be the units of a to b of v of t dt? Well, if we said the area under the velocity curve is distance traveled, or displacement, and v of t is given in feet per second, we're talking about change in position. A change in position would only be measured in feet. That seconds time would not apply to the actual value of that integral because we're talking about distance. Distance is not a measurement of time. Distance would need to be feet. Alright, in part C, so let's actually evaluate this thing. From 3 to 8, 3t squared plus 2 dt. That would equal, from 3 to 8, 3t squared plus 2 dt. We're going to plug in 8 into our position function. So 8 cubed plus 2 times 8. That would be our finishing position. And we're going to plug in 3. And evaluate this. Evaluating 8 cubed plus 2 times 8 gives you 528. Minus evaluating 3 cubed plus 2 times 3. That gives you 33. And if you subtract these two things, you get 495. Now, an important idea, I asked you for a thorough explanation. So we know that this thing equals 495, but we need to think about what is 3 and what is 8. Those are the times of our finishing and starting position. So if I was going to provide a thorough explanation, I would say the particle moved 495 feet from 3 to 8 seconds.